We just looked at antiderivatives and a definite integral. And now we're going to get into our new chapter, which is on integration. And we're looking at integration right now as area under a curve. But before we do that and just kind of give you the formulas, we have to kind of talk about how we got there, just like we did with derivatives and limits and how we're looking at the slopes and getting closer and closer and closer. We're going to have that kind of same idea with finding area under a curve. So first thing is, if we have some shape like this and we're trying to find the area under the curve, this could be difficult. So the problem is find the area of the region of R bounded below by the x-axis on the sides by the line of x equals A, so you can see in the picture, and x equals B. We want to find that area. We're given that the curve is continuous, and we need to know that. And we're given that we're going to be looking at it bounded between the x-axis and the curve. And so for right now, we want to know that that curve is above the x-axis. We'll talk about it later when the curve is not above the x-axis, but for now we're going to look at it. Later we'll talk about it below, but now we're going to concentrate it on above, and you'll know why in a minute when I start going through this. Okay, so we want to find this area in here. So what we're going to do is we can estimate this area, and we can get better and better estimations. So first of all, maybe if I break this down into shapes that I know how to find the area, we can do that and estimate the area of those shapes inside. And so we can use different shapes, but a lot of times we use rectangles. And we know that the area of a rectangle is base times height. So if we can create rectangles in here, and so maybe let's do 4 different rectangles. Actually, I'm going to do more. So let's say that we got rectangles in here. Let's do 1, 2. I'm going to change it a little bit just so it's 3. So if we do a rectangle, we want to somehow hit the top of the curve. And then there's different ways to do that, and then we'll talk about it in a minute. But let's say that we look at hitting on our interval, our first interval here. Let's make a rectangle and let it hit the top of the curve on the right-hand side. So I'm going to take this, I'm going to do a horizontal line. I'm going to make a rectangle. So basically, I can figure out what this area is. Well, how can I do that? I can figure out what this value is by looking at f of, let's say that this is maybe x sub 0, x sub 1. So x sub 1 value. That's my height in there. My length in here, I need to figure that out. So let me again look at how many, and let's just draw our rectangles as we're at it. So if I go to my next interval, hit where I hit the graph, I'm going to have a point there. Go to my next interval, hit where I hit the graph. This is going to be the height of my rectangles. So if I do that, oops. I probably should have done all my vertical lines first. It just would help me draw this. And you'll see why I have pictures and this takes a while. Like right here. And I am doing the right one. So I have to go to the right. And we're gonna just assume that these are all equal intervals in between so that the base is the same. Okay. So looking at my rectangles, we can now figure out approximately what this area is. So for this first rectangle, we know what that area is. We know it's base times width. We need to figure out what that width is, and how we're going to figure out what that width is let's figure out how many rectangles we have, and we're going to look at it with the length. So I know this length in here is equal to B minus A, right? Because I know that this length in here is B. And if I subtract off my A value, that would give me that length in here. Okay, so that's my B minus A. But I need to divide it into 1, 2, 3, 4, 5, 6 different intervals. I have 6 rectangles in there. And that is going to give me the length of one of these bases. They call this delta X, triangle X. Okay, so let's write this out. We know the area of this triangle one, or not triangle, sorry, rectangle one. This is equal to B minus A all over 6. That's our base, times our height, which we said the height of that rectangle would be the same y value of this function. So f of x sub 1. Now let's look at the area of the rectangle 2. So let's say that this occurs when x is 2, x sub 2. So I can say that my area of 2 this is equal to the base, which is still b minus a all over 6, times this height. Well, this height of this rectangle, that's the y value on my function when x at x sub 2. So this is going to be f of x sub 2. So we're going to keep doing this. So the area here, this would be my area 3. Area 3, this is going to be my base, which is b minus a all over 6 in this case, times this height, which occurs at f of x sub, let's call this x sub 3. So notice that you keep doing that. So this will be x sub 4, this will be x sub 5, and this will be right here, x sub 6. So total area or estimate is equal to area 1 plus area 2 plus area 3 plus area 4 plus area 5 plus area of 6. In our case, triangle X is always equal to B minus A all over N, where N equals the number of triangles. Why do I want to call them triangles? I don't know, but they're rectangles. Notice that each one of these areas has that base. So we can technically factor that out, right? So I can say my total area is equal to the base, which is b minus 8a over 6, all times, well, we have to look at the height of each piece. So the first one was our y value at x sub 1, plus our y value at x sub 2, plus our y value at x sub 3, plus our y value at x sub 4, plus our y value at x sub 5, and our y value at x sub 6. So that gives me the approximate area under this curve. So you can tell in some ways my rectangle looks like it's a good approximation. Here, my a sub 2, I'm cutting it short, right? There's a lot of this area above that I'm not calculating. A sub 3, it looks like I'm cutting it short. A sub 4, I'm overestimating my area. And so, and I can continue on in that manner. Notice that we'll see that the more rectangles we have, the better estimate of that area under the curve we can get. So just think about it. If we had an area under the curve, let's say this fell under the curve, and we were looking at thinking about height, that doesn't make sense because this y value is going to give me a negative number. So again, we'll talk about that later on in this chapter, but let's go through on how to do these things. Okay, so here's the steps. First thing that we want to do is we are going to subdivide our interval, or what we want to find the area of, into n separate subintervals. And they'll tell you in the problem, you know, cut it up into 2 rectangles, cut it up into 3 or 9 or 10 or whatever. But n is the number of rectangles you're going to have, and we're going to subdivide it into n of those. And that's going to be this equal width for each one. And so again, we find delta x, that's equal to b minus a all over n. Okay, so we split up in different rectangles by looking at b minus a all over n. So that was one step. The next step, on each subinterval, you're going to draw a rectangle to approximate the area of the curve under that subinterval. Okay, so there's different ways that we can make these rectangles, and we'll talk about the different ways that we can do that in a minute. And I'm just going to give you the idea behind all of this. So once you've drawn your rectangles, after you figured out how many you're going to have, created your subintervals, made your rectangles, we know that the width of any of these rectangles in here, that width is always going to be delta x. And we said that that delta x again was the length of this divided by how many rectangles you're going to have. The height of each rectangle, that had to do with the point that we're hitting. Notice in this that the height is not on the right endpoint. And we'll find that it actually doesn't matter where you choose your value to be. And then we're going to look at the area of the kth rectangle, and we're going to sum the area of each one of those. But you find the area of any of these rectangles by looking at the y value of the height of the rectangle, by plugging in that x value that you're using, times the base, or the width of that rectangle, which we know is delta x. So we did that. We found the area of every rectangle. And so once we find the area of each rectangle, we're going to sum them up. And that will give us an estimate. Okay, so there's different methods of doing this. Let's just, before I get to the different methods of how to find the height of your rectangle, this information right here, this can get tedious on how we're writing it, right? Summing up all these rectangles. What if we wanted 1,000 rectangles? So to have to write that out, it will be really tedious. And so I don't know if you remember, but it's something that we'll touch on tomorrow and talk about, but summation notation. That means that we're going to sum things. And so if we can express this, we have our base delta x all times our function f of x, and we're going to evaluate it at these values where we have the height. So we can call it x of I. We can look at x starting at 1, depending on left or right, when we'll talk about that in a minute. And there's going to be n of them. And so that's another way that we can write the area. So the area of that would approximately be that. And so we're going to look at that tomorrow. We'll look at limits as n goes to infinity. And so if you don't remember about summations, you might want to re-look at that before tomorrow's lecture. Okay, so one way of looking at this is looking at the upper sum method. And the upper sum method is saying that when we're looking at one of your rectangles or any of the rectangles, you're going to look at the maximum y value in that rectangle. And so if you look at this interval right here of my C values, oops. Here's C sub 1. Let's see. Oh, this is the interval too, sorry. So this is one interval in here. If you look at this, notice that the highest point on this curve, on that section, is when X is here. And so they're going to choose for the upper sum method, this to be the highest point in your interval. So another instance, if I looked at this interval right in here, and I'm looking at the highest Y value that this occurs on, notice that highest Y value occurs right here. And so that's how they choose the height of that rectangle. So if we're choosing the highest point, notice that this is going to give me an overestimate of what the area is. So looking at the following, we have a graph, and we want to find the area under that graph using the upper sum. So notice the more rectangles that we put under this graph, the better that this is looking, the better that area, approximation of that area is. Notice that when we have 125 rectangles, this looks pretty good approximation, a lot better than when we had 12 rectangles. But the more we got, the better it looks. And so see where we're going with limits here? If we can have this n go to infinity, then we are going to pretty much have the exact, or we will have the exact area under the curve. That's where we're approaching. Okay, so that was the upper sum method. We have the lower sum method, and so that is actually looking at this, and when we have our rectangle, we're looking at the lowest point that we're hitting. So the lower sum method is the absolute minimum of y equals f of x on whatever interval we're looking at. So if we're looking at this kth interval right in here, and I wanted to look at the lowest value, y value that this graph hits, it would be right here on that interval. And so that would be the height of this rectangle. So if I decided to choose this piece, well, any piece we choose, you're just looking at the lowest place it hits. So it'd be here, and that would give me the height. Notice that when we use the lower sum method, this is underestimating the area. And again, you can see that the more rectangles you get, the better approximation we're getting of that area under the curve. So what about, instead of looking for the highest y value in that interval or the lowest y value in that interval, why don't we choose the minimum or the midpoint, or the left-hand side of that rectangle or the right-hand side of that rectangle? So just some things to remember what I just said or reiterate. The lower sums, they use the point on the interval at which the f attains a minimum. That y value is a minimum, a rectangle of minimum height. The upper sum, they use a point in the interval at which that f value, y, attain is that maximum, rectangle of maximum height. But really, which I was just trying to get at, any point x of 0 in a subinterval can be used to determine the height of f of x of 0 of a representative rectangle. Notice when we're getting 125 rectangles in here, that's getting so close to each other, it doesn't really matter what is that y value. It's pretty much the same because there's so many. Okay. So other commonly points that are used when you're trying to find the height of that rectangle, and this is how I learned it, was using one of these. So other commonly points chosen are either the left-hand endpoint of your subinterval, the midpoint of that subinterval, or the right-hand endpoint of that subinterval. So this is what it looks like if we're looking at the midpoint method. So here is one interval, and you would choose the halfway mark in that interval to give me the height. Here's my second rectangle. So I will look at the midpoint between these intervals to give me this height. So I would continue on until I get to the last interval. I would look at the midpoint between the end and start of that rectangle and take the height of the midpoint. So that's one method. If we looked at the right-hand method, we're looking at first interval, we're looking at the right-hand side of that interval and finding that y value is our height. Look at the right-hand side of the second rectangle. That gives me my height. Right-hand side of the third one, fourth one, so on. The height is the x value at that right-hand side of that rectangle. So guess what? The left-hand endpoint method, we're looking at the left-hand side of our interval. That is going to give me the y value, is going to give me the height of that rectangle. The left-hand side of the rectangle gives me the height. So it doesn't matter which height you use. They're all going to give us an estimate, and the more rectangles we use, the better we're going to get. Okay, so we're going to use the lower sum of two rectangles to approximate this area under the curve of 1 over x between x equals 1 and x equals 5. So we want to find the width, and the width or base of our rectangle is our b value, which is 5, minus our a value, which is 1, all over how many rectangles we're trying to get, in this case 2. So this distance in here is 4 over 2, which is 2. So this is going to hit right here. This is going to hit right here. Since it's asking me to do the lower sum, I'm looking at the smallest y value that this is hitting. I notice that this function is decreasing everywhere, so that lowest y value is going to be my right-hand part of that interval. So to find this area, this is approximately the base, which is 2, times the height, which in this case would be f of this y value here is 3, plus this base, which is 2, and this height here is a f of 5. So looking at that, we have this is approximately, or this is equal to, or approximately 2, f of 3, well, that's 1 over 3, plus f of 5, so 2 times 1 over 5. So I have 2/3 plus 2/5. Common denominator is 15. And so rewriting 2/3 with a denominator of 15, that would give me 10/15. Common denominator 2/5, or equivalent fraction with a common denominator of 15, that is going to give me 6/15. So this is going to equal 16 over 15. Okay, so we found that our area is approximately 1 1/15 units squared. But notice if we broke it up into 4 rectangles, our change in x, this is going to be 5 minus 1 all over 4. 4 over 4, that's going to give me 1. So instead, if I take this, oops, that's going to be the next thing we were getting at, but we're not going to get there. If I do this now and split it up into 4 separate rectangles, lowest point, and we found those area, that area is going to be, this distance is 1, all times f of x of 1, which is going to be 2, plus f of 3, plus f of 4, plus f of 5. And so we could plug that in, plugging it at our values into our f of x function, which in this case is 1 over x, to get an approximate value if we had 4 rectangles. So you can do this too for the upper bound. If we did the upper bound, in this case, instead, you would have used your left-hand side endpoints. That's the highest value. Okay, so we'll get a little bit, do a little more of these tomorrow, but then we're also going to jump into looking at doing this with taking limits as those subintervals, those rectangles go to infinity, so that we can get an exact answer.